Hello, calculus fans. So we just talked about how to compute the surface integral of a scalar field across a parameterized surface. But of course, sometimes our surface is just the graph of a function. In fact, that's sort of the simplest expression. So as an example, maybe our surface is just given by z equals g of xy, some function of two variables. Then we can write down a very simple parameterization. We can say x equals x, y equals y, and z equals g of xy. And we'll say that the values of x and y come from some set D. Then if we think of this parameterization as a vector function, then the derivatives with respect to x and y are these things. So r sub x is equal to I plus dg by dx k, and ry equals j plus dg by dy k. And if we cross those and compute the length, we'll get the square root of dg by dx squared plus dg by dy squared plus 1. All right, that's going to give us an integration formula. This is a computational formula for how to compute the surface integral of a scalar field when the surface is just the graph of a function. So we'll get the double integral of f of xy, and then we replace z, of course, with g of xy, and then we have to multiply by the square root of dg by dx squared plus dg by dy squared plus 1. And now this is just an ordinary double integral. All right, let's do an example. We're going to compute the double integral over s of x squared ds, and s is the surface given by this function. Z equals 2/3 x to the 3/2 plus y to the 3/2. And let's just say that the values of x go between 0 and 1, the values of y go between 0 and 4. So our surface is defined by this function g of xy equals 2/3 x to the 3/2 plus y to the 3/2. And the partial derivatives of this function are very simple. dg by dx is just x to the 1/2, dg by dy is y to the 1/2. And that means when we compute that square root expression, we're going to end up with the square root of x plus y plus 1. So that's not terrible looking. Let's go ahead and evaluate the integral now. We end up getting that the surface integral of x squared ds is equal to, so we'll just get integral from 0 to 1, those are the x limits, integral from 0 to 4 of the original integrand x squared times square root of x plus y plus 1. Notice that if we had a z in here somewhere in the original integrand, if we had a z anywhere in there, we would have to replace that with our function g, which was, what was that? 2/3 x to the 3/2 plus y to the 3/2. Now, this particular integral can be evaluated in MATLAB. You get a pretty ugly looking expression, although MATLAB handles it fine. I'm just going to go ahead and leave it at that out of laziness. Okay, that's all for now.